Alright, so far we've built the foundation. We've talked about the roads and the engines of the internet like latency, bandwidth, and how TCP ensures our data actually arrives in one piece. But here's a real question that most people gloss over. When your browser opens up YouTube, what language are we actually speaking? We know the connection is there, but what exactly is being whispered or shouted over the TCP connection? That's exactly what we are breaking down today. It's time to move past the hardware and the transport and get to the actual conversation. Now we have finally reached the top of the stack, the application layer. This layer is the rulebook. It defines the request and response formats, headers, authentication, and error handling. It is the language. Whether it's HTTP, WebSockets, gRPC, DNS, or SMTP, without this layer, apps wouldn't understand each other. It would be like getting a phone call where both people are just screaming in different languages. So, if the application layer is a language, we need to look at the one that built the modern web, HTTP. At its heart, HTTP is a simple request response protocol. It's like basically you ask for a video and the server sends it back. To master HTTP, you need to understand the four pillars that hold it up. First is it is stateless. Think of the server like it has amnesia. Every time you click a link, it's like meeting the server for the first time. It doesn't remember you unless you bring a name tag along with it, which is exactly why we use cookies, sessions, or JWT tokens to maintain state. Second is the methods. These are like the verbs of your request. You use get when you want to fetch data, post when you're submitting a form, and put or a patch when you are updating existing information. These methods tell the server exactly what action to perform. Third are the status codes. These are the server's way of giving you a status report in three digits. Say 200 OK is the green light we all want, 401 means you're logged out, and infamous 404 means you're looking for something that isn't there. And finally, headers. These are the fine print or metadata of the request. They carry crucial instructions like content type. Basically, it's like telling the browser it's an image or the video. Authorization, they are basically keys. And cache control, which determines how long your browser should save a copy of data before asking the server again. But the plain HTTP is like sending a postcard where anyone can read it. To fix that, we use HTTPS, which is HTTP wearing a suit of armor called TLS. So TLS provides encryption, authentication, and integrity. Through a quick handshake, your browser and server verify each other and lock the connection down. In modern system design, HTTPS isn't just a nice to have feature, it is a mandatory. And the protocol also evolved for speed. HTTP 1.1 was slow because it mostly handled one request at a time. HTTP 2 fixed this with multiplexing, letting us send many requests over a connection. And we have HTTP 3, which is built on Quick and UDP. It ditches the old TCP baggage to give us faster handshake and better performance on mobile networks. Today, for large scale systems, HTTP 3 is the gold standard. But what if the server needs to talk to you without being asked? For things like chat apps or live sports scores, we use WebSockets. So it starts like a HTTP request but upgrades to a persistent bidirectional TCP pipe. This allows the client and server to push data to each other instantly anytime without the heavy overhead of repeated HTTP requests. WebSockets are for the front end, but what about the back end? When different servers needs to talk to each other as fast as possible, we use gRPC. Developed by Google, gRPC uses protocol buffers instead of JSON. Because it's binary, it's smaller, faster, and strictly typed. That's why many large systems use REST for their public face but rely on gRPC for everything happening behind the curtain. And finally, we have DNS. Think of it like a GPS of the internet. When you type youtube.com into your browser, your computer actually has no idea where to go. Computers talk in IP addresses, humans talk in names, and DNS is a bridge between them. It's a lightning fast relay race. If the address isn't in your local cache, your computer reaches out to the recursive resolver, which hunts down the answer by jumping from the root server to the TLD server, like .com, and finally to authoritative name server that holds the actual IP. But in modern system design, DNS is much more than just a translator. It's a traffic controller. Through geolocating routing, DNS can send YouTube server closest to the physical host to reduce latency. It also handles failover, that is, if a data center in New York suppose goes offline, then DNS can instantly redirect all the traffic to Virginia. Without it, the web wouldn't just be hard to navigate, it would be impossible to scale. So let's put it all together. What actually happens when you open YouTube? First, DNS resolves the domain into the IP. Then a TCP connection is established. Next, the TLS handshake secures the connection via HTTPS. Your browser sends a HTTP request. A load balancer routes it to the right place and the server responds. As the video chunks start delivering, a WebSocket might jump in to handle your live comments, while deep in the data center, internal microservices are shouting to each other via gRPC. All of this, the handshake, the security, the routing, happens in just a few hundred milliseconds. Here is the bottom line. If you don't understand application layer protocols, you can't design scalable systems. But now that you know how these apps talk, we can finally look at how they are built. In the next video, we are moving into APIs and microservices architecture, where these protocols become the literal building blocks of the real world systems you can use every day. I'll see you there. Thank you.